And record. Okay. Here we go. On our Moodle page, I have to apologize. I actually could have sworn that I had posted assignment 15 and Excel assignment 10. And then I had a panicky moment when I went on today and it said it was hidden. So they're available now. I hope you enjoyed the break, the assignment break. But then because I had that panicky moment, what I did, and don't be overwhelmed, well, be excited, don't be overwhelmed. But I did post all the remaining assignments. Okay? So they're there as you're plugging away through them. It's over. Right? Just get them out of the way. And so assignment 15 and Excel assignment 10, those are the material that was in that video that I posted, right? Chapter 7, sections 1 and 2. We'll do a review, of course, right? But what I want to do is today do section 7.3, which is kind of the biggest mumba jumba in chapter 7, the difference of two means, right? And so then we'll have seen all the materials. And then what I have planned for Thursday is we'll do review of chapter 7, right? And so just kind of introduce all the things and then review it in that one class where we go through a couple of questions. They're so long when I talk about them, and we don't have time to do a lot of them, but we'll have time to do one of each, right? One sample mean, paired data, and then the two sample means. So today we're doing two sample means. So assignment 16 can be from paired data or the stuff today. Kind of put them into one assignment, and then another bonus assignment on the ANOVA, which we're not covering, but if you want to boost your assignment grade, otherwise it'll be dropped. Further review on Thursday, we'll be going through the questions in the chapter 7 review, inference for numerical data practice. There's a lot of kind of redundant words in there, but those are the questions that we'll go through together in class. And so it might be nice if you have a chance to try them in advance before we go through them together. I understand that it's a busy time, so that's totally fine, but it might be nice to try it on your own, see how it goes, and then we'll do it together. But wait, there's more. Oh, I did a weird thing, didn't I? Now that I'm zoomed in. I posted practice for test 2. It's a lot of practice. All the different types of questions. I do want to highlight. Oh no, I fixed it. Yeah. And so there's going to be 4 questions from this list of possible test topics. So you need to be prepared for all of them, of course. But there's no way I could possibly have a test testing you on all these things. And so, right, and so it's got a little summary up at the top, and then all the questions. And I posted the solutions, but this is where I did something. I don't remember doing that, but you have to mark the practice for test 2 as complete. But I think that's pretty easy to do. I can change that setting, I guess. But I think you can just say it's completed, right? I'm pretty sure. And then it'll open the solutions. But wait, there's more. I also posted a PDF version and a Word document version because by popular demand in the past. And so it's a decision tree for all the different types of inference questions that we could have, okay? And with a little reminder up at the top. Okay? So the type of question can be either a proportion question or a means question, right? So categorical data or is it numerical data, right? And then from there, if it's a proportion question, you could have one sample proportion. You could do a hypothesis test or a confidence interval. You have to check the conditions, which I've listed. You'll notice that they're almost the same across the board, right? And then where does that put you on the formula sheet, right? Use it, don't use it. I posted the Word document in case you want to make any changes to it yourselves, right? And so it's there. And with a reminder, if the p-value is less than the significance level, then you have enough evidence to reject H0. Just kind of summarize all of chapter 5, 6, and 7 on one page, I guess. Right? A couple of things here. Like I said, so for means questions, we could have one sample mean. We could have two samples that are paired, right? That's that special case that we introduced, or I introduced in the video from last week. Okay. Paired data behaves like one sample mean once you calculate the differences. And you could have two independent sample means, which is what we're talking about today. And then finally, three or more groups. If you want to compare the means, you use what's called an ANOVA, analysis of variance, but we're not doing that. It's there for completeness because it's in the textbook, but we're not going to do it. So there's the Word document, in case you want to manipulate it yourselves. Oh, and there's the bonus assignment, but I think I already pointed that out, okay, on the ANOVA, in case you're interested. You can do it, right? It introduces a new test statistic called the F test statistic. But everything else stays the same. From the F statistic, you get a p-value. Everything else stays the same. But like I said, I'm not going to test you on the ANOVA. Because I'm here, looking forward. You've got your test 2 on Tuesday, right? It's on chapters 5, 6, and 7, which is essentially just 6 and 7 because chapter 5 was just a kind of a slow motion version of 6.1, right? And so it's really chapter 6 and chapter 7. And then we get into chapter 8, which is lines of best fit. You get to leave hypothesis testing and confidence intervals behind for a little bit. It's a really nice way to end the term because everyone kind of enjoys, it's called the regression, but lines of best fit. After all that inference, hypothesis testing and confidence intervals. Right? So it's nice. Last two real assignments, assignment 17 and Excel assignment 11. And in the final week, I have posted a bonus Excel assignment, which is on multiple linear regression, and then a bonus assignment 4 on statistical process controls. Those are both bonuses, right? But if you do them, they'll replace a lower assignment grade. So if you missed assignments. I'm also making the two Poisson assignments bonus, even though they weren't labeled that, which means I think there's a total of 7 assignments being dropped. It's a lot, but that's okay. Should have good assignment grades. There. Perfectly manageable. The end is creeping up on us. But here we are today. Last bit of new material before the test. All right. Oh, and I have a reminder. Test number 2, in case you missed it, is on Tuesday. And I do want to do a little bit of review from the video that you watched. For sure. Got it done. Or maybe you just read the notes. I don't really care. We introduced one sample mean as well as paired data or matched pairs. Now I've lined them up like this to illustrate and to emphasize that, okay, if I'm talking about mu, right, if I'm trying to estimate what mu is, the population mean, then my best guess for what that is my sample mean, x bar, right? When we're talking about means, right, we use the t distribution. Now we have been working with the t-table already, right? And so now we're just working in, where's the t-table here? We're just working in the rest of the table, right? And these are all t's now. So we've been working down here at the z star line, right, to find our critical values for our confidence intervals, to find our p-values, and we do the same thing, but now...
ماني جوعان.
Let me just mute everyone here. How do I mute everyone? There. Okay, good. Oops, wrong spot. Here. Yes. So now we use the table in the exact same way that we have been doing. The only difference is that the t distribution, we have these degrees of freedom. Because the shape of the t distribution depends on our sample size, right? And so the bigger our sample is, the more kind of condensed our curve is, right? And it becomes a normal distribution. Otherwise, it looks exactly the same. And as a quick reminder, let's see down here. So if you find your exact degrees of freedom on the table, you use that. If you find that you're choosing between, let's say, 30 and 40, what do you have to do? You have to round down, right? Even if you have 39 degrees of freedom, which is closer to 40, you have to go to 30, okay? Because otherwise you're pretending that your sample size is larger than it is, and that's a problem, right? And so you always round down if the degrees of freedom is not in the table. But if you look and actually compare the values here, right, they don't change that much. Right? And so even though it kind of feels like it hurts in a weird way to round down, right, don't worry, it doesn't change anything. So for t's, really the only change is, okay, now instead of being at the z star line, let's pretend that you have 19 degrees of freedom here. Then that's the only line that you can look at. Everything else goes away. You can use it to find the critical value for, let's say, a 95% confidence interval, 2.093. You can use it to find p-values, right? Try to place your calculated t somewhere on this line and then map it down to your one-sided or your two-sided p-value. Right? And we'll work more with the t distribution today, so don't you worry. Down here, I have the degrees of freedom for a one sample mean question is just your sample size minus 1. So the t star is your critical value for your confidence interval, and then S is your sample standard deviation, and of course N is your sample size. The hypothesis test for one sample mean is that mu is equal to some number, right? Is mu equal to 5 in the example that we did, right? Or is it less than 5? Right? Then you calculate your t, which looks a lot like a z, right? It's just now I have my X bar. How far is my X bar from my hypothesized mean? Taking into account the standard error of X bar, S over root N. What's really nice for means is that the standard error for the confidence interval is the same as for a hypothesis test, and that's going to be true for all the means questions. Whereas for proportions, right, we had to figure out, okay, do I use my p hat or my p naught, right? That kind of thing. Now, if you compare side by side a confidence interval, remember the trick for paired data is you calculate the differences, right? If you have two observations on the same subject, we consider them paired, right? So then we can calculate the differences, and then we have one sample of the differences, right? And so then we're analyzing mu diff. Now notice everything stays the same except for little subscript diffs everywhere, right? For the differences, for the differences, for the differences. Right? Otherwise, everything stays the same. What's nice about if you have paired data, then the null hypothesis will always be that mu diff is equal to 0, right? Because if you want to compare two groups, right, before and after scores from a test, for example, right, then if they're the same, then the difference would be 0. If they're not the same, the difference would not be 0. Right? So it's kind of a special case of the one sample mean. And again, the degrees of freedom is the n diff minus 1, so the number of differences that you have minus 1. So they are the same. And for both of these, the conditions, just to recap, for one sample problems, right, whether that's just a one sample that you want to compare to a number, or maybe it's one sample of differences, the conditions are the same, and they're a lot simpler than anything that we saw for proportions, right? And so our conditions for both of these, we have the first condition, which is the independence condition. If you've randomly sampled, you're allowed to assume that all these observations are independent of each other. So randomly sampling allows us to assume independence. Now, if you have paired data, the whole reason we got to paired data is because they're not independent, right? You've got these pairs on the observations. But what we mean here is that the differences have to be independent of each other. So the participants in the study have to be randomly sampled. So it still applies, just slightly different. The normality condition, if the sample size is greater than 30, you're allowed to just assume normality. And so it's kind of two-pronged. So if n is greater than 30, we may assume normality. We're allowed to have smaller sample sizes, right? We just have to put in a little bit more work. So if n is less than 30, I guess less than or equal to 30, okay, we need to, let me move that. We need to make sure that it looks approximately normal, okay? Or we have to assume that it looks approximately normal. So if n is less than or equal to 30, we need to check the distribution, I'm not even going to go to normality. I'm going to say the distribution is not extremely skewed, right? Which is even more lenient than saying it has to be normal, right? Check the distribution is not extremely skewed. If it is, then in that case, you wouldn't be able to use the t-test, which is what we're learning about. So of course, we'll be able to assume that it's not extremely skewed. So we need to check / assume. I'll add that in here. Assume the distribution is not extremely skewed. Nice. All right. Any questions about that? So we'll do more examples of the one sample mean and the paired data, but on Thursday. So we'll introduce the two sample means today, and we'll come back and review it all. But any questions before we start this next section? Okay. All right. So the difference in two means, and I usually like to emphasize two independent means. Just to show that, hey, I can have two groups with two different averages, and I want to compare those two. In fact, I would argue that this is the most common piece of statistics that you'll use in real life, okay, is the two sample t-test. So this is called AKA a two sample t-test. I only bring that up because as you go through your schooling, you maybe see some more stats, right? Read some articles, that kind of thing. You'll see we used the two sample t-test, and we did this, and we did this, and like I said, I would argue it's the most common thing that we use in statistics. So what is it? Well, I'm going to, before we introduce the example, I want to do the same thing that we've been doing, where we just kind of break down what's on the formula sheet, right? And talk about it. And then I will point out that we're getting so close to the end. I know it felt like we'll never get through this. But then this is just that line of best fit stuff, which we'll do after the test. So this is the last of the material that's on the test. I'll bring it in. Beep. So we can talk about it. So two sample means is going to be the type of problem. Now, if you have two samples, it means that you have two groups, right? Each of them is going to have a mean, each of them is going to have a standard deviation, and each of them is going to have a sample size. And what's really fun and cool is that the sample sizes, they don't even need to be the same. That's neat, right? And so each group has, X1 bar, S1, and N1, X2 bar, S2, and N2. We've seen that before, right, with the proportions, P1 hat, P2 hat, N1, N2, right? And so we're no strangers to being overrun with notation, but the subscript denotes which group it comes from. Just as before, when we were working with two sample proportions, it doesn't matter which group you assign to be group 1 and which one you assign to be group 2, as long as you're consistent, of course. You don't want to mash them up. Okay? Because it needs all this information, right? 6 pieces of information that I have to give you in order to answer these problems. That's usually kind of a dead giveaway for the type of problem, right? You start reading the problem and you say, oh, this group had a mean of this, and this group had a mean of this, and this group had a standard deviation of this, and this group. So there's a lot of information that I have to give you, right? And so, right, because part of your job for test 2, as well as the final exam, is read a question and figure out what type of question is it. And for 1 mark on each of the questions, I'll ask you, what type of question is it, right? Mostly because that's something that you should be doing anyways, and also to encourage you to say, okay, I need to know the types of questions, okay? And it's gonna just help being able to figure out what type of question it is, because then you can focus on that area of the formula sheet, right? Once you've told me what type it is, even if it's wrong, right, just kind of stick with it. It's going to be kind of hard to stick with it if it's the wrong type, but as long as you kind of tell me, hey, I'm going to treat this as this type of question, so I'm using this part of the formula sheet, I'm actually happier with you doing that than kind of jumping all over the formula sheet. Right? So tell me what you're doing and then do that. Stick to your guns. Okay. So, bless you. Let's see here. There was something else I wanted to say here, but I'm sure it'll come to me. This, as before, this is just theory, right? Can ignore that it's true, and it is something that we're relying on in our formulas, but that's more for me. I would feel like a fraud if I don't put it on there, but that's not for you to worry about, right? And so here, x1 bar minus x2 bar, that's the difference of the 2 means, right? The difference of 2 means is what we're analyzing. Follows a norm. I guess I shouldn't have scratched it out until I talked about it. Follows a normal distribution. Hey, that's great, right? Centered on the difference between mu1 and mu2. Nice. With a standard error of the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. We don't have sigma because that's the population standard deviation. And we don't have mu because that's the population mean. If we had either of those, we wouldn't be doing any statistics at all, because what's the point, right? That's okay. We use x1 bar minus x2 bar as our best guess for mu1 minus mu2, right, as our point estimate. And then when we replace this sigma squared, right, we're going to replace it with the sample standard deviation because that's my best guess, right? And that's what's going on in these formulas here, right? Instead of sigma 1 squared over n1 plus sigma 2 squared over n2, I've replaced the sigmas with my best guess from my data, right? Which is s1 squared over n1 plus s2 squared over n2. And so here, this is the standard error of x1 bar minus x2 bar. You don't need to worry about it, but when we're replacing our mu's with our best guess, which is x bar, and our sigmas with our best guess, which is s sample standard deviation, right? We're making 2 replacements, and we're used to just making 1, right? But that's the reason we have to incorporate the t distribution instead of the z. It's because we have these 2 things that are sample dependent. Forget it. There, I said it though, for completeness. Oh, I remember what I wanted to say. I will give you all these values in the question. Otherwise, you won't be able to do it. Huh? Usually, we organize it in a table. I think it's on the practice 4 test 2. I have it sometimes in a table, right? So you can start to recognize it, and also in a big paragraph. So you can start to recognize it that way. Just exposing you to the different ways that we can kind of frame these questions. But besides that, this is exactly how all our confidence intervals are built, right? My point estimate plus minus a critical value, this t star. Now, in order to find the t star, I need my degrees of freedom. But besides that, that's all right. I can find my t star. And then times the standard error of my point estimate. So even though it looks big, right, we just need some way of incorporating all this information. Right? Scrolling down to the bottom, T star, we said, requires the degrees of freedom. For questions that we're doing by hand, so all these that we're doing, we're going to use the minimum of n1 minus 1 and n2 minus 1. If you're using software, it'll use a more complicated formula. But for us, this gives us a good approximation. Right? It's good enough. What does this mean? The degrees of freedom, if it's the minimum of 2 values, right? If I ask you, hey, what's the minimum of 2 or 5? It would return 5. No, 2. That was an honest mistake. I wasn't trying to trip you up. So it's the smaller sample size, smaller sample size minus 1. Is really what it's saying. All right. I'll do the example that I managed to muck up. The minimum of 2 or 5 is equal to 2. So if you ask for the minimum of a list of numbers, it'll return the minimum. So depending on your smaller sample size, right, that'll determine your degrees of freedom. And then it's just that sample size minus 1. Same rules apply if you're stuck on the t-table and your degrees of freedom aren't there, then you have to round down still, right? So all the same things that we've already covered. For hypothesis test, we're testing for mu1 minus mu2, right? What does this thing look like? We've seen something similar when we talked about P1 minus P2, right? Comparing 2 proportions. And we have 2 options again. They're very similar to what we saw for proportions, right? My null hypothesis is that mu1 is equal to mu2. These 2 things are the same, right? Until I have proof otherwise, I have to assume that they are the same. And I want to highlight the or here because it's just whatever you prefer. Or you can use mu1 minus mu2 is equal to 0. The difference between the 2 means is 0. That kind of traces back to the paired data as well, right? If I have 2 groups and they're the same, then the difference should be 0. Okay? I think this one kind of leads nicely into our test statistic T, right? Because technically, and we've seen this before, right? For two sample proportions, technically we take our point estimate minus our hypothesized value, assuming the null hypothesis is true, right? But if we're assuming that mu1 minus mu2 is equal to 0, right, which we have to do, then that's why it's not on the formula sheet, right? Because it's always just going to be minus 0. Okay? So how far is the difference in our means, right, from 0? Taking into account the standard error of the point estimate. Now again, notice that this whole square root, this big square root that you have, is the same as this square root here, right? Which means that if you are, for some reason, doing a confidence interval and a hypothesis test in the same question, you can recycle some of that work, right? You don't have to do it twice. All right, good. But this I'll highlight as equal to 0. Okay. That's not so bad. Let's see what an example looks like. Well, any questions before we do? Our example is about diamonds. So in case you're unaware, weights of diamonds are measured in carats. Okay. Now, just for our calculations, we're going to say that 1 carat is 100 points, and 0.99 carats would be 99 points, etc. I'm not entirely sure why they made that adjustment, but we'll just go with it. Now, the difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the human eye. So we really can't see the difference between these two things. So what we're interested in, does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? Do with that what you will, right? We'll kind of talk about what that means if that's the case, but that might be kind of useful to know, right? And so I've got a question for you, because here we're talking about, does it tend to be higher than the price of a 0.99 carat diamond, right? What does that mean in terms of my alternative hypothesis? I would want to know, well, first we have to assume our null hypothesis is that mu of 1 carat diamond is equal to the mu of 0.99 carat diamonds. Right? We have to assume that they're the same, right, on average. Whereas this bullet says the alternative hypothesis, we want to know if mu1 is significantly higher than mu of 0.99. Versus the next point says this. We're going to test to see if there's a difference between the average prices of 0.99 and 1 carat diamonds, kind of contradicting this, because then what would the alternative hypothesis be here? My alternative hypothesis here would be that mu1 is not equal to mu of 0.99. And I'll point out, we've seen this before, right? As soon as we have two samples, two independent samples, then we need to use kind of question-specific subscripts, right? We can't use the generic 1 and 2 unless it is a convenient group 1, group 2 situation, right? So then we use question-specific subscripts, but you only have to use the question-specific subscripts in your hypotheses, right? So not too bad, because I need to know what you're talking about. Okay, so my question, well, no one likes answering questions. So, and I don't mean that in a bad way. I never answered questions as a student. That's why I never asked questions. I wouldn't dare. No. I ask hypothetical questions that I answer right away. Which one of these should we do? I'm more interested in this one, probably, right? Because if I learn that there's a difference between the two, right, I guess I could do a confidence interval to learn what the difference would be. That might be nice. But let's see here. I'm gonna see what the okay. Which of the following is the correct set of hypotheses for testing if the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? So we'll use that first one then. But I wanted to highlight the change in the wording, right? And how that would change your alternative hypothesis here. But we're going to use this one. Nope, this one. Now they rejigged some stuff in order to be able to compare equivalent units. What we're going to do is we're going to divide the prices of 0.99 carat diamonds by 99 and 1 carat diamonds by 100, and then compare the average point prices, right? Because then we have a price per point that we'll be able to compare. The data looks like this. These are the point prices. I'll clarify here. Point prices. So the distributions of the point prices for the 0.99 carat diamonds looks like it tends to be a little bit lower than for the 1 carat, right? Because here the minimum of the 1 carat diamonds is roughly at the same, well, it's actually higher than the first quartile for the 0.99 carat diamonds, right? The median looks like it's roughly the same though, right? And so we can use these side-by-side box plots, which it's been a while, I know, right? But we can use them to get an idea of what these groups, how they compare. Okay. Like I said, because there's a lot of information that I have to give you, right? Often I'll just summarize it in a table, right? And so here's one way that I could summarize it. So the 0.99 carat diamonds, right? So the 99 point diamonds had an average point price of 44.5, so $44.50 per point. Now, of course, remember there's 99 points to each diamond, so multiply that by 99 for the total price, right, on average. But we're going to compare the point prices. Standard deviation of 13.32, and here we have a sample size of 23. For our 1 carat diamond, so the 100 pointers, we have an average point price of 53.43. Standard deviation, slightly smaller, 12.22, and a sample size of 30. I will point out here, because it always trips people up, but notice N1 and N2 are allowed to be different. We've seen that for the two sample proportions as well, but it's nice to point out. So here we have our summary statistics, all the things that we need in order to be able to answer some questions. Now, of course, our parameter of interest, the average difference between the point prices of all 0.99 carat and 1 carat diamonds. So in this case, if we're talking about 0.99 and 1 carat diamonds, usually I do it in the order that matches how the data was given. Versus up here when we were talking about it, notice how I did the 1 carat and then the 0.99. Doesn't matter, right? As long as you're consistent. So to be consistent with the rest of the slides, let's use this 0.99 carat diamond as group 1. And this as our group 2. And I want to compare those two. It's not going to change anything, right? It's just going to make your positive t a negative because it would flip to the other side. But besides that, switching the groups is not going to change anything, as long as you're consistent. So the parameter of interest, right, is the population difference in the carat prices. So mu of 99 points minus the mu at 100 points. And then we have our point estimate, x1 bar minus x2 bar, generically. So that's going to, these values are going to come from our data that we've been given up here. So loud. So which of the following is the correct set of hypotheses for testing if the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? They've done it in a weird order, but looking at the options here, they've got the 99 pointers on the left and the 100 pointers on the right. And so if I grab this here, copy. We're so used to seeing this by now. Probably. But this is the reason they have the 99 here and the 100 here. Even though they talk about that, the 100 versus 99, it's kind of backwards. But matching this order, group 1, group 2, then my null hypothesis is going to be the mu of the 0.99 is equal to mu1. And if I want to know if mu1 is higher than mu of 0.99, then I have this mu 0.99 is less than mu1. Which means it's a one-sided test, right? It's always nice to remind yourself up here in the alternative hypothesis, if it's a one-sided p-value or a two-sided p-value that you're looking for much, much later, right? Because you're only concerned with one extreme. Right? Now what you're doing is you're saying, okay, 44.5 is less than 53.43. That's a fact. Okay? But what we want to know is if it's significantly less, right? And so that's what this alternative hypothesis is talking about. And which of these, let's see here. I have not equal to, well, it's not that because, oops, because of this. It's not that B because of the inequality is not where I want it to be. Everything else looks good. It is C. What's wrong with D though? Let's talk about that. D is bad because I don't hypothesize about my sample means, right? Like I said, I know for a fact that 44.5 is not the same as 53.43. So trying to say that they are is kind of weird, and I don't care about that. I'm trying to use that to learn about my muse, right? And so here, our hypotheses have to be about the population, right? So here, the bad part, right? Hypotheses must be about the population. Right? We know everything that we need to know about the sample. That's not interesting. So there's no sense in hypothesizing about something that you already know everything about. Okay. Nice. Now before I guess we'll do this and then I'll recap what the conditions are. The conditions are the same as for one sample mean, which means that for independence, right, I need to have randomly sampled, but for both my samples now, right? And my two groups have to be independent of each other, right? So the independence is kind of two-factor now. And my sample sizes, each, if they're greater than 30, cool, okay? If they're not, that's okay, as long as we can assume that they're not extremely skewed. Okay? So, which of the following does not need to be satisfied in order to conduct this hypothesis test using theoretical methods, which are the only ones that we have in this course? Point price, or the point price of 1.99 carat diamond in the sample should be independent of another, and the point price of one carat diamond should be independent of another as well. So this I would translate to, we need independence within each sample, and that's true. So that's not that one. Point prices of 0.99 carat and 1 carat diamonds in the sample should be independent. That's true because I'm using a two sample means technique. So how I would summarize this is I need independence between the samples. Independence between the samples. If you don't have independence between the samples, then they would be paired. Hey, where's my pointer? Right? Which would make it a paired data type of question, right? Which would change your analysis. So this one is also a go for our analysis, and something that we would need to check. The distributions of point prices of 0.99 and 1 carat diamonds should not be extremely skewed. That's broad strokes, not even talking about the sample size being less than or greater than 30, right? This summarizes it in general, right? Even for small sample sizes. And so this is true. Making the last one false, but why? Both sample sizes should be at least 30. That's not true, right? It's easier to check the assumptions if they are, right? But as long as the distributions for both groups are not extremely skewed, it's okay, right? And so here, can still use smaller sample sizes as long as C, which is this guy here, is satisfied. Now, conveniently, we have the side-by-side box plots. So what we're looking for is we just want to make sure that they're not extremely skewed. So if we go back to those side-by-side box plots, we can talk ourselves into it. What would it look like if it was extremely skewed? You would have, yes, we do have kind of a tighter distance from the median to the maximum than we do from the minimum to the median, right? Whereas if we had a normal distribution, it would be kind of symmetric around the median, of course. But in general, I don't see any outliers, right? Outliers would give me a skewed distribution, right? And so I don't have any outliers in either of these distributions. So I feel comfortable saying that neither of them are extremely skewed. Good. Yeah. Any questions about those conditions? Okay. As we've seen on your formula sheet, but I wanted to bring it in because I went and hunted down the actual degrees of freedom formula, just in case you're interested. And so if we have two sample means, then we calculate a t, and the t is a test statistic, and all test statistics have the same layout. You have your point estimate minus your null value divided by the standard error, and I'll put a little subscript here of the point estimate. Now, the standard error of the point estimate is S1 squared over N1 plus S2 squared over N2. We've already seen that because we've talked about the formula sheet already, right? And so they're just introducing it. And we're going to use the degrees of freedom as the minimum of N1 minus 1 and N2 minus 1, right? The smaller sample size minus 1. I will highlight here that the calculation of the degrees of freedom is actually much more complicated. In fact, here it is. This is not something that you're unable to do. It's just way too tedious for what you're getting, right? It's not something that I want you doing. But what is it? Well, it's S1 squared. Well, I'd have to give you S1, right? Square it. I have to give you N1 already, so you have that information. S2, same thing. You have that information. N2, fine, you have that information. S1 again, N1 again, N1 again, S2 again, N2 again, N2 again. You have all these components, right? But look at all that work. That's brutal. We don't do that. You don't worry about that. Okay? But I bring it up so that you can be grateful that we're just taking the smaller sample size -1 instead. And so here we're going to use this degrees of freedom. If you're searching online, it depends on what field you're in. Sometimes they use N1 plus N2 minus 2, which we're not going to do. If you tell me that that's what you're going to do, I'll be fine with it, right? But on your formula sheet, we'll have you have the smallest sample size -1. And so here we use the smaller sample size -1. But if you're using software uses this. Especially if you're using Excel, right? Excel will use this as its degrees of freedom because it can. It's not hard to program, right? It's not even hard to calculate. It's just tedious. And so, right, just be aware that it'll use slightly different degrees of freedom than we do. Okay. Now, I think we're ready to actually do, let's answer this question. Time to go rogue. Where should I put it? Maybe here. No, here. Is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? Now I am going to snag where the data is and maybe rephrase the question potentially again. Do you see the problem? They don't match. Here we're introducing 1 carat diamonds followed by the 0.99 carat diamonds, and here we have 0.99 followed by 1. And I just want them to match. How about this? I'll do this instead. Might be easier. Copy. Paste. Wait, that's big. I just moved them over. Otherwise, it's so irritating. All right. Now we can do it. Is there evidence that the average point price, now the 1 carat diamonds are my group 1 and my 0.99 carat diamonds are my group 2s. Let's put this here. That the point price is higher than the average point price of 0.99 carat diamonds. Now, is there evidence? Means that I have to do a full hypothesis test, right? And so we'll do it. Let's do it together, just start to finish. I'll start with the most boring step, 0 conditions. We already talked about them. I want you to see them in action. We have the independence condition still. I have to make sure, or I have to argue rather, that my observations within each group are independent of each other. Okay? So we assume both samples were randomly sampled. Reasonable? Okay? We assume both samples were randomly sampled. That's independence within the groups. My sample of 1 carat diamonds have nothing to do with my sample of 0.99 carat diamonds, right? And so that's how we arrived at, okay, these are 2 independent samples that I want to compare, right? And so that's the independence between the 2 groups. And so the 2 groups are independent of each other. So that's the independence between the groups, which we've seen before with the 2 sample proportions. For the normality condition, we have the side-by-side box plots, right? And so from the side-by-side box plots, we see that neither distribution is extremely skewed. We see that neither distribution is extremely skewed. And that's enough to satisfy that normality condition, even though one of our sample sizes is only 23, that's okay, right? Because we looked at the distribution and we saw, it's not extremely skewed. So a lot simpler conditions, but they are different from what we're used to, right, for the means. All right. Now the actual hypothesis testing. Right, step 1 is state the hypotheses my null hypothesis, right, is, and now that I've moved the data around to match the order, right, then I'll talk about 1 carat versus 0.99 carat. Right? So mu of 1 carat versus mu of 0.99. I first have to assume that they're equal to each other. Or, if you prefer, what's the alternative here? Or I guess I shouldn't say alternative like that, because we're leading into the alternative hypothesis, which is not what I meant. Mu1 minus 0.99 is equal to 0. They're the same, right? They're saying the same thing. And so if they're equal to each other, then yeah, the difference would be 0. So you pick and choose whichever one you want. The alternative hypothesis In this case, we want to know if mu1 is higher, significantly higher than 0.99. It does require a smidge more work, in my opinion, if you're comparing the difference to 0, right? Because then if it depends on how you calculated your difference, right? But we're taking mu1 minus mu 0.99. So if mu1 is higher, consistently higher than mu of 0.99, I would expect the difference to be greater than 0. Right? Or if you just subtracted the mu of 0.99 over to the left, that's going to give you the same thing. But I do think it does require just a smidge more thought if you're talking about the difference versus 0, right? As opposed to just comparing them to the two straight across. But it's up to you, whichever one you want. I will make a note here. All right. If we're talking about two groups, right, two sample proportions or two sample means, we have to use question-specific subscripts. Okay, and I'll give myself another line here. When comparing two groups, right, that can be either proportions or means. We must use question-specific subscripts. I know I wrote a note when we talked about two sample proportions as well, right? But you have to use question-specific subscripts. Otherwise, I don't know what you're talking about in the hypotheses. It's too annoying to do it in your formula for T, but in your hypotheses, you have to. And so here, right, this is what I'm talking about here. Mu1, mu 0.99. Okay. Good. Got our hypotheses. We've got a one-sided test, right? Because I'm only concerned about one extreme. So I'll say down here, this is a one-sided test. We don't need that until we find the p-value, but we will need it. And it's one of the biggest disconnects. It's a really common question that I get is, well, how do I know if it's a one-sided or a two-sided test, right? And so if you have a less than or a greater than, you only care about one side, it's a one-sided test. If you have a not equal to, you're concerned about both sides, making it a two-sided test, right? It's one of those things that it feels really weird and hard to understand until you get it, and then you don't really know what the problem was. But it's just one of those things. Everyone struggles. We've got our hypotheses. Step 2, do the test. Really, it's calculate the test statistic, right? For two independent sample means, T is going to be x1 bar minus x2 bar divided by the square root of s1 squared over n1 plus s2 squared over n2. Technically, how far is it from a hypothesized difference of 0? But we just dropped that, right? If you go back to your formula sheet, it's not even on there, right? Oh, and I guess I could bring that in. But it's in my brain. Hmm. Okay. So now we calculate the test statistic, our t, right? And so kind of out in the real world, usually if you are doing a hypothesis test where the test statistic is a t, we call it a t-test, right? And so you can start throwing that around. Oh, t-tests and stuff like that. Everyone will be like, oh, yeah, I got you. T-tests, of course. Everyone's doing t-tests. It's true. Everyone. They're always doing t-tests, even when they shouldn't be. All right. We have all this information, right? And so I'll go grab it. I moved it around a little bit. Copy. Paste. This is our X bar, this is our S, and this is our N. So X1 bar, X2 bar, S1, S2, N1, N2. 53.43 minus 44.50 divided by the square root of 12.22 squared divided by 30 plus 13.32 squared divided by 23. Now you want to make sure that you use or do the square on each of these standard deviations, right? If you forget to square it, you're going to get a small standard error, which will give you a really big T. Right? And so if you're getting a really big T, that can happen, but it is worth checking your math, right? Did you remember to do the squares? Right? Also, if you forget to take the square root, it would change your T quite a bit. So what are my numbers? 53.43 minus 44.5. Let's do that one first. I get a difference of 8.93. Really what we want to know, and over something I haven't calculated yet, really what we're seeing is how far is a difference of 8.93 from 0, right? That's what we're really testing. Okay. Taking into account the spread, right? Maybe if the spread is huge, 8.93 is not that far from 0, right? Whereas if the spread is really small, 8.93 would be far from 0, right? And so it all depends on what the spread is, and the spread is the standard error. Now, I want you to be really methodical when you work through these calculations. You don't have to show your work because that's often more tedious than actually just doing it in your calculator, right? But you want to make sure that you do 12.22 squared divided by 30. And then if you have a store function in your calculator, that might be a good time to use it. Do the 13.32 squared over 23, then add them up, then take the square root. So, or use a ton of brackets, right? And so that's another alternative. 12.22 squared divided by 30. Now I have a store function, so I'm going to use it. 13.32 squared divided by 23. Oops. Plus, and then square root that. And I will write down what I get because I feel like I fumbled. 3.562531.505. Now, if anyone else found this standard error to be different, please tell me now. so I don't go through with the wrong number. That'd be bad. Seems to be okay. All right, so 8.93 divided by that guy, I get a t of 2.50664499. Now, since we're using the t-table, it only has 3 decimal places for t, right? So that tells me I'm allowed to round to 3 decimal places. So t is roughly 2.507 to 3 decimal places. If you wanted to, you could keep all the decimal places, right? But this should be okay. All right. 2.507 is kind of hard to gauge. We've got this internal kind of a cutoff of 2, right? A z plus minus 2 would be considered significant most of the time. T behaves a little bit different, right? We have a little bit more wiggle room for T, but I suspect that at 2.5, I'll be rejecting the null hypothesis. I suspect, but let's see. Step 3, find the p-value. Now, in order to find the p-value, I need my degrees of freedom. And so first I write out using the t-table with degrees of freedom equal to the minimum of n1 minus 1 or n2 minus 1, which is, I can do it down here, which is the minimum of 30 minus 1 or 23 minus 1, which is the minimum of 29 or 22. Well, the minimum of 29 or 22 is 22. Huh? If you wanted to write it out in words, that's totally fine, right? Using the smaller sample size of 23 minus 1 as my degrees of freedom, that's totally fine, right? I just prefer the shorthand of the minimum function. So we have 22 degrees of freedom. Now I have to use the t-table. And first thing I'm looking for is, well, do I have a 22 degrees of freedom line? I do. That's always exciting. It simplifies things a little bit. So from here, I need to place my calculated t on this line. And I'm going to bring in all of this, even though it's going to be quite big. So we use the same layout as before. The absolute value of t, which is equal to 2.507, notice how I've centered it because it's going to fall between 2 values. And just as before, we don't have to deal with it in this question in particular, but the end cap here would be 0, and the end cap here on the other side would be infinity, just like we had on the Z star line. Right? So it behaves the same. So now, oh, it's a close one too. 2.507, right, is going to be between 2.183 and 2.508. So let me zoom out just a little bit here, right? This is going to be in here. So I write 2.183 and 2.508. if it was actually on the one of the values, you would need to revisit the unrounded value, right, to see which side it would go on. It'll never be exactly one of those values. It will put you on one side. But that's pretty rare that it's so close to one of the boundaries. Tempting to just use 2.508. Tempting. We won't. Although in real life, I'd say you could, but not for this course. Learn good habits here. Okay. So our t, somewhere between 2.183 and 2.508. That's great. Now, this is where I need to remember if I have a one-sided test or a two-sided test, right? So this is the disconnect, because this is where you need to scroll all the way up to the top and look at your alternative hypothesis. I'm only concerned about one side, so it's a one-sided test. So what I'm looking for is a one-sided p-value. And if I trace this down, I find that my one-sided p-value is somewhere between 0.01 and 0.02. So we write that down. The one-sided p-value is between 0.01 and 0.02. I like to write my inequalities in the same way, right? And it also reads nicer. If you always are reading from smaller values to larger values, that's proper. And so that's why I use these inequalities here. But it does mean, just as before, right, you have to read the p-values from right to left because they're decreasing as you move out. So now I have my p-value. It's somewhere between 0.01 and 0.02. Now I'm ready for my conclusion. Do I have enough room? Maybe if I give myself just a little bit of more space, just maybe one line. This might be all I need. Let's move this over here so I can bring this back up here. Oops. Oh, yes. Your conclusion. Are you reciting your conclusions in your sleep yet? They're all the same, right? You compare your p-value to your alpha level. What's our assumed alpha level? We use 0.05. I don't remember one given to us, so we'll use 0.05. No, there wasn't. So we'll use an alpha level of 0.05. Right? And what does that mean in terms of your null hypothesis? Right? And then what does that mean in terms of the question? All right, here we go. Since our one-sided p-value, right? Remember, it's your job to show off all the things that you know, right? Since our one-sided p-value is between 0.01 and 0.02, we have oh, sorry, not yet. It is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught, which means we have enough evidence to reject H naught in favor of HA. Therefore, now we want to rephrase the question as an answer. All right, here we go. Way up here. There is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. Oh. Therefore, there is evidence that 1 carat diamonds, or sorry, the average point price, I think they specified. Yeah. Which would translate to 1 carat diamonds being more expensive, but there is evidence that the average point price of 1 carat diamonds is higher than 0.99 carat diamonds. Hmm. Can do with that what you will, right? If a 0.99 carat diamond is significantly cheaper than a 1 carat diamond, and we can't tell the difference, I think I personally would just choose to buy a 0.99 carat diamond because I'm cheap like that. Or, I don't know. Again, it's not my job as a statistician. I just present, here are my findings. Now you figure it out. You do with it what you will. Huh? Nice. All right. So, how am I doing? Okay. That's good. I think it's going to be perfect. So then we did it together, of course, the way I want you to do it. But then the slides do a short version. Blah, blah, blah. But we did it all together. Of course, you can use Excel. So this is our code, but in Excel, if you have a t distribution, right, it needs to know what the t is, and it needs to know what the degrees of freedom are. And so I think it's t.dist of your t, and it wants to know the degrees of freedom. Yeah.
Why does it say it's between 0.01 and 0.025?
I feel like they used a different table because we don't have 0.025, do we?
Do, but then that would
Oh,
0.074.
I suspect that their table maybe doesn't have the 0.02. This one. I think our table is bigger. Good catch, though. Didn't even. I'll make a note. Thank you. This is using a different table. They're using the table in the textbook, but I actually don't like it. I prefer this one because it gives you all the p-values and stuff. Makes you work less. There is also a t.test function. And so I encourage you to play around with the t.test function. It's in the Excel assignment, right? But it requires the raw data, right? Which is nice. But then it does all the calculations kind of on the inside and just returns a p-value. Okay? And it also uses that fancy degrees of freedom calculation, which we're not using. So of course, if you want the actual p-value, you would use some sort of software. And we already did our conclusion, right? We rejected H naught, and the data provide convincing evidence to suggest that the point price of 0.99 carat diamonds is lower than the point price of 1 carat diamonds. So, I mean, you've got some options. Maybe buy a 0.99 carat diamond. Who are we to say? Last thing I want to point out is the confidence interval. And so what is the equivalent confidence level for a one-sided I think they mean confidence interval. Or at least that's what we were calling it. I think level works too, but the equivalent confidence interval level, I guess, for a one-sided hypothesis test with an alpha of 0.05. Now this is going to require just a smidge of thought here. We had a positive t, right? Which puts us on the positive side of 0. So here we had a value. And what we said is if this area is less than the alpha level of 0.05, then I'm going to reject H naught. We found that our value was somewhere out here, right? T equal to 2.507. So we rejected H naught. But notice that this 0.05 is smooshed all into the one tail, right? Because we're doing a one-sided test. If you're doing a confidence interval, though, the confidence interval has to be symmetric about the center, right? Which means that we would need to also force 0.05 down here in this tail for the symmetry. So if you want your confidence interval results to match your hypothesis testing results for a one-sided test, then you have to tack on the alpha level on the other side as well. Okay? Which means if I have 5% here and 5% here, then I've taken away 10%, which means that I'm left with a 90% confidence interval in the middle. And so therefore, a 90% confidence interval would be equivalent to a one-sided hypothesis test with alpha equal to 0.05, which is what we did. And otherwise, what you'll find is that the results don't necessarily match. So there it is. So if you wanted to make a 90% confidence interval, for a 90% confidence interval, we still need our degrees of freedom, which we said is the minimum of 29 and 22, which is 22. That hasn't changed. So then my T star for a 90%, well, they do call it confidence level. Anyways, whatever. 90% confidence interval, at 22 degrees of freedom, my T star would be 1.717. Let's see here. I'll bring it in. 22 degrees of freedom. Turns out it's in a really inconvenient spot on the table because both the screenshots are really large. But if you want a 90% confidence interval at 22 degrees of freedom, there, the T star would be 1.717. Again, they're using a sloppier table with only 2 decimal places, which is fine. But you'll have the one that we're working with, which has 3. In Excel, there's a T dot inverse it needs the probability to the left as well as the degrees of freedom. Okay? And so if you want a positive t for your critical value, right, then you would use t dot inverse of 0.95 for a 90% confidence interval, right? And so, right, because the area to the left would be 90 plus 5 or 0.95. So here, this is the area to the left of t, or t star, for a 90% confidence interval. But you would get the same number. This is just our code. Because I'm running out of time, you can build the confidence interval, but I'll just use what they've done here, right? Our confidence interval from our formula sheet is this guy here. No. We've got our point estimate. We've got our critical value times the standard error of the point estimate. And they've used some rounded values, but that's okay. This is the difference in the average point prices, right? And so we're 90% confident that the average point price of a 0.99 carat diamond is $15.05 to $2.81 lower, that's from the negatives, right, than the average point price of a 1 carat diamond. So slightly different interpretation, or if you prefer, right, we are 90% confident the difference in average point prices that's not the interval. Sometimes I mix it up, but I shouldn't do that. The interval from negative 15.05 to negative 2.81 captures the difference in average point prices. That's fine too, right? That's using the same layout that we have been using, right? This version requires a little bit more thought about, okay, well, what does a negative mean? How did I calculate the differences, right? How does it translate to the different groups, right? So this first one is totally fine. Okay, there's a recap, but also section 7.4 we're not doing because it's power calculations and we don't need to do that. And then 7.5 is comparing more than 3 or more means with ANOVA, which is not tested. I'll highlight that part. But there is a bonus assignment if you're interested. Do you have any questions? Let me know. Otherwise, see you on Thursday.